Many people's knowledge of quantum physics starts and ends with the so-called Schrödinger's Cat Paradox, one of the most famous and mind-bending thought experiments in quantum mechanics. It was thought up by Austrian physicist Erwin Schrödinger in 1935. The purpose of this paradox was to demonstrate the odd nature of quantum superposition, wherein particles can exist in multiple states simultaneously. It goes like this. Imagine placing a cat inside a sealed box. Within the box there is a radioactive atom with a 50% chance of decaying within a certain period. If the atom does decay, a Geiger counter inside the box will detect the radiation and trigger a mechanism that releases poison, killing the cat. If the atom doesn't decay, the poison isn't released and the cat survives. But here's where things get really weird. According to the currently accepted principle of quantum mechanics, until someone actually opens the box to observe which of these two outcomes occurred, the cat exists in a superposition. It is both alive and dead. This dual state continues until the moment of observation when the superposition collapses into a single reality. Only at that point is the cat truly dead or alive. The longer one thinks about it, the more difficult it can be to wrap one's head around. Indeed, Schrödinger's cat illustrates one of the most baffling aspects of quantum mechanics, that observation itself plays a fundamental role in shaping reality. While this little philosophical puzzle has had a profound implication on modern physics, it is also heavily tied to what we call the multiverse or many worlds theory. A cat that's both alive and dead may seem strange, but physicist Hugh Everett came up with an even more surprising idea in the 1950s. In his many worlds interpretation of quantum mechanics, the wave function doesn't collapse into one single outcome. Instead, every possible outcome already exists in its own parallel world. So, in the case of Schrödinger's cat, there would be one universe where the cat is dead and another where it is alive. There is also one in which the triggering event has happened yet, one where the box failed to disperse and the cat became radioactive, and one in which the cat escaped the box altogether. The theory at work here is that each time a quantum decision is made, whether at the level of atoms or at grand cosmic scales, the universe splits into multiple realities, each representing one of the possible outcomes. As mind-boggling as this may seem, it offers an elegant solution to quantum mechanics' measurement problem. Instead of collapsing into one reality, the universe simply branches into many. Of course, the word simply in that statement is doing a lot of heavy lifting. In order to get a better idea of why this is so profound, it's necessary to re-explore the principles of quantum mechanics. Quantum mechanics isn't exactly the sort of topic one takes a crash course in. Fortunately, these ultra-complex topics have been explained in layman's terms, often enough that it's possible to get the required understanding in just a few minutes. For starters, quantum mechanics describes how matter and energy behave at the smallest possible scales, the realm of atoms and subatomic particles. It exists because while classical physics, like Newtonian mechanics, works well for everyday objects, it fails to explain the strange behavior of the impossibly small products that actually form the building blocks of what we call reality. There are a total of 5 main principles at work here. First, there is wave-particle duality. Particles like electrons and photons can behave both as particles and as waves. In the former, they are an object. In the latter, they are spread out over space. This duality is meant to explain phenomena like light's ability to act as a wave during diffraction or interference and as particles when it interacts with matter, such as the photoelectric effect. Next, there is superposition, the topic from the Schrodinger's cat experiment. Superposition describes how a particle can exist in multiple states at the same time. For instance, an electron can occupy several different energy levels or locations simultaneously until it is measured, at which point it assumes a single state. The next principle is what's known as entanglement. As the name implies, this is when two particles become entangled, meaning that their states are linked. For this reason, measuring one particle instantly determines the state of the other, regardless of the distance between them. This mysterious phenomenon troubled Einstein, who famously referred to it as spooky action at a distance. Speaking of Einstein, one of his contemporaries was a physicist named Werner Heisenberg. He claimed that the uncertainty principle states that certain pairs of properties of a particle cannot be measured with absolute precision at the same time. For example, the more accurately we measure a particle's position, the less accurately we can measure its momentum, and vice versa. As with Schrodinger's cat, it's the measurement or observation that all of the variables determining or collapsing our reality lie. Quantum mechanics doesn't deal in certainties, but in probabilities. Before we measure a quantum system, it exists in a superposition of all possible outcomes. It is only when we measure the system that one of these possible outcomes becomes reality. While quantum mechanics may seem abstract, its applications are highly practical. Right now, researchers and even commercial businesses are utilizing quantum computing, which leverages superposition and entanglement to process information in ways that classical computers cannot. With quantum cryptography, which offers unparalleled security by making use of quantum mechanics principles. Even semiconductors and the electronics that power our everyday devices rely on quantum mechanics to function. The point of this is to state that this is not just scientific existentialism. There are indeed real practical examples of these theories working in our world. While Schrödinger's cat is often used to illustrate the mind-bending nature of quantum mechanics, it's important to understand that Schrödinger himself didn't actually agree wholeheartedly with the theory. In fact, Schrödinger specifically designed the cat thought experiment to point out the absurdity of applying quantum mechanics to everyday objects. In quantum theory, a system's wave function evolves smoothly over time, according to the Schrödinger equation, when no one is observing it. However, once a measurement is made, that wave function collapses and is replaced by one of the possible outcomes. Schrödinger found this idea unsettling, so he created his famous thought experiment to highlight the contradiction. After all, could something as tangible as a cat really exist in a superposition of both life and death? Schrödinger's frustration lay not so much in the theory being wrong, but in the fact he felt it was incomplete. He believed that quantum mechanics couldn't fully describe reality, at least not as we experience it. Proponents of the many worlds theory believe that their explanation fills the gap Schrödinger thought was missing. The wave function in question never collapses, it simply branches into every single possible outcome, all of which then occupy their own specific universe. Schrödinger's cat isn't simultaneously alive and dead in one universe, but it exists in separate realities where both outcomes are true. But for this to be true, we must accept that there are infinite universes, because every single observation ever made by anyone will cause a similar split. There are various ideas about the multiverse, both cultural and scientific. These ideas are usually quite different. Cultural ideas focus on human life. People often think about what their lives would be like if they had moved to another city, chosen a different career, followed other hobbies, or been in a different relationship. They imagine the path they didn't take and try to picture how things might have turned out. Cultural multiverse ideas are more focused on individual experiences and choices. They're not concerned with the physical possibility of alternate universes, but rather with the metaphorical exploration of different life paths. This reflects our understanding that life is a series of choices, each potentially leading to drastically different outcomes. The cultural notion of a multiverse often stems from our innate tendency to wonder, what if? In science, the multiverse concept is divided into the quantum multiverse and the cosmological multiverse. The quantum multiverse tries to explain what happens when measurements are made in quantum physics and how human life connects to the quantum world. It suggests that people may be living in multiple realities without being aware of their other version or doppelgangers. The cosmological multiverse suggests that a process called inflation, which is the rapid expansion of the early universe, happens frequently, not just in our universe, but in others. This leads to the creation of bubble universes that keep expanding, and while our universe has also expanded, these other universes are now beyond our reach. Why do physicists think the multiverse could be real? It's because the properties of our universe seem to be just right for galaxies, stars, planets, and life to exist. If certain constants, like the strength of gravity or electromagnetic forces, were slightly different, planets and life wouldn't have formed. This idea is known as the fine-tuning problem. Physicist Brandon Carter proposed an idea around 1970 to explain this fine-tuning. He suggested that maybe our part of the universe, or even the entire universe, is special in some way. We should consider all the other possible universes and ask why we are in this one, rather than another. It might be because there are many possible universes and we happen to be in one of the few that can support the formation of stars, planets, and life. In most of the other universes, life as we know it wouldn't exist. A challenge with these other universes is that, if they exist, we can't perceive them. Right now, scientists don't have a way to directly test the multiverse theory. Some have suggested the ideas for indirect tests, hoping that, in the future, we might find clever ways to do direct experiments. But for now, the fact that the multiverse is untestable means we don't have solid proof. It remains a theory without a way to confirm it through current scientific methods. There are other ideas in physics that can't be tested directly. For instance, because the universe is expanding and light has a limited speed, we'll never be able to see parts of the universe beyond a certain distance, about 46 billion light-years. Beyond that, we can only imagine what might be out there, and there could be surprises we'll never discover. Quantum uncertainty also limits what we can observe. Due to Heisenberg's uncertainty principle, we can't, even theoretically, measure the exact positions and movements of all particles in the universe at the same time. Physics has reached a point where many things aren't directly measurable. If we create a theory that explains everything in the observable universe and requires a multiverse, some scientists would accept that we may never know everything. Others might continue exploring different possibilities, refusing to accept those limits. Most people would agree that it would be ideal to have a theory of the universe that's self-consistent, covers everything, and doesn't rely on things we can't observe, but that might not be possible. Some researchers argue that if something can't be tested in the usual scientific ways, it isn't real science, it's pseudoscience. For you, the question is whether the goal of science is to discover the truth about the universe or just to focus on things that can be proven through experiments. We've already covered how every time a quantum system is measured, it collapses from a superposition of multiple possible states into a single outcome. The wave becomes a single particle in a fixed state. But what exactly constitutes a measurement? More importantly, why does it force the system into a definite state? This was Schrödinger's primary issue with quantum mechanics as it was understood in his time. As stated, the many worlds interpretation posits that no collapse happens at all. Every possible outcome of a measurement occurs in its own parallel universe. Yet this is not a perfect explanation, because each observer world would experience just one outcome. In a different reality, another observer might experience a different one. This would mean that there's no such thing as an actual event, and may essentially destroy Descartes' philosophy of I think, therefore I am. You are, but you also are not at the same time. Recently, more scientists have come to accept that measurement outcomes might differ between observers, leading to subjective realities. For example, two observers could witness the same event, like flipping a coin, and experience different outcomes. One might see heads while the other sees tails. Obviously, this ambiguity raises profound questions about the very nature of reality. If different observers can experience different outcomes, does that mean there is no single objective reality? For the many worlds interpretation to hold true, reality itself would have to become subjective. However, as stated, this means that every quantum event down to the smallest interaction creates new parallel worlds. Nothing really happens, but at the same time, everything happens at once. Nothing is real, but at the same time, everything is real. In quantum theory, the lowest energy state for space-time, where everything happens, including the possible multiverse, is called a vacuum. But if space between universes is always expanding, it can't be a true vacuum. There must be some energy driving the expansion. Quantum field theory, which combines quantum theory and Einstein's special relativity, suggests there are multiple vacuum states, but most are false vacuums, not the lowest energy level. Since nature seeks to lower its energy, a false vacuum isn't fully stable, meaning it's metastable. In the quantum world, things can sometimes tunnel to a lower energy state, like a marble jumping from one valley to another without going over the hill. Cosmologists are interested in this process, called false vacuum decay, because it could explain how the universe and other universes began. The early rapid expansion of our universe matches the idea that it started as a bubble, which formed when the cosmos tunneled to a lower energy state, a phase transition, before reaching a true vacuum. This is way beyond the scope of this video, but it's worth mentioning because it highlights just how complex and mind-bending the nature of the universe can be. However, for now, the important takeaway is that these theories about vacuums, energy states, and phase transitions help explain the possibility of multiple universes and how our own universe may have started. While it might seem abstract, these ideas are crucial in shaping our understanding of reality and the cosmos. It's important to note that Schrödinger's cat is not the only paradox out there attempting to help people better understand reality. In the 1960s, physicist Eugene Wiener extended the cat discussion in a way that makes more sense in lieu of the multiple worlds theory. Known as the Wiers Friend scenario, he asked his fellow physicists to imagine observing the Schrodinger's cat experiment in the lab. From his friend's perspective, the cat is in a superposition of both dead and alive. The moment the friend observes the cat, the superposition collapses into a definite state, either dead or alive. From the friend's perspective, this is the reality. But what if we take a step back and consider another person outside the lab, Wiener, who doesn't yet know the experiment's outcome? Until Wiener checks in on the first observer, Wiers Friend, both the friend and the cat exist in a superposition. If Wiener's friend observed a definite outcome, why does Wiener still see a superposition? This raises the unsettling possibility that consciousness itself might be subject to superposition, with observers being entangled in multiple realities until their observations are confirmed by another. A recent experiment conducted at Griffith University pushed the boundaries of Wiener's friend by using quantum entanglement. Remember, this is the phenomenon where two or more particles are linked or entangled in such a way that the state of one directly influences the state of the other, no matter how far apart they are. In the Griffith University setup, two particles were entangled, meaning the measurement of one would instantly determine the state of the other. The team observed that the results violated Bell's theorem, a principle that sets limits on the correlation between entangled particles if quantum mechanics follows established rules. A good analogy for the experiment and its implications would be to imagine two synchronized clocks, one placed on Earth and the other on Mars. Normally, you'd expect them to keep time independently because of the vast distance between them. However, in Griffith's experiment, these clocks are magically linked. Whenever you check the time on Earth clock, the Mars clock instantly shows the same time, even though no signal traveled between them and they are millions of miles apart. Now imagine that people have always believed these clocks must follow certain universal rules, like Bell's theorem, which says they can't show the same time if nothing connects them at faster than light speeds. Nevertheless, the clocks stay perfectly synchronized, breaking the rules of how we currently think time or reality works. This discovery implies one of two things. Either our rule that information can't travel faster than light is flawed, or more radically, the idea that both clocks exist in the same singular reality is incorrect. Humans have a strong desire to understand everything in our world, and now that includes everything in the universe. We're a bold species living on a small planet compared to the vastness of everything else. We use tools like theoretical physics and direct observation to try to make sense of it all. We hope these methods align, but there can be delays. Sometimes experiments give results that theories can't explain, and sometimes theories, like general relativity, are so convincing that we accept them without proof, and only later do experiments catch up. There are exciting theories that take time to test, so patience is needed. But if a better theory comes along that matches experiments, people will move toward it rather than waiting for the old theory to be proven. Theorists have their own preferences, and what one researcher considers a limit might be different from another. Personal philosophy plays a role. Even in science, people have their own preferences. Even trained physicists working with general relativity and quantum physics have room for personal views. For example, some believe time is an illusion, while others think time is real. This leads to philosophy because it's impossible for us to step outside time and see if it's an illusion or not. We can only speculate whether time truly passes or if space and time are on equal footing and our sense of time passing is just in our minds. We've covered a lot of ground so far, diving into some pretty wild theories about the universe and beyond. But don't worry if your brain is feeling a little scrambled. This stuff is complex and we're just scratching the surface. The key point is that even though we're dealing with ideas that sound like science fiction, they're based on real scientific principles that help us explore the deeper mysteries of existence. Thanks for watching. Be sure to check out my other videos on quantum mechanics, and I'll catch you in the next one.